Okay, this is a Matrices question. It's 2018 question 6. There's a fair bit to it, so I've already written it out and we'll just talk our way through it. First one is nice and straightforward. It says calculate AB. This is A, this is B, nice and straightforward. We multiply through this times this, this times this, this times this, this times this, and it gives us that. So that's A and that's B. Part 2 says, using the matrices A and B, demonstrate the commutative law, that the commutative law does not hold for matrix multiplication. Nice and straightforward one here, as long as you know what that means. It means that if you do A times B, that it's not the same as B times A. A times B, we've just done it, gives a 2 by 2. If you rearrange these, you're actually going to get a 3 by 3 whenever you multiply them out. It's not going to give the same answer, therefore it's not commutative. Nice and straightforward one there. Part B, a system of equations is given by those three equations where U and W are real numbers. Find the values of lambda for which the system has a unique solution. If it has a unique solution, then the determinant is not equal to 0. Weird things happen whenever the determinant's equal to 0. So the determinant we can work out like this, and by putting it not equal to 0. So we're doing lambda times this, take away this times this. That's what I have up here. Minus 1, remember it's a minus, upon then minus 6 upon take away 10 lambda minus 3. That's here. And then the third bit we're doing 0 times all this, so it's just going to be a 0. If you multiply through all this and tidy it all up, you have 7 lambda squared minus 17 lambda plus 6 is not equal to 0. Factorizing gives us this. That means our two values that don't work are going to be lambda or 3/7 and lambda is 2. So as long as lambda doesn't equal this or this, then you will get a unique solution. The next wee part then. It says, if lambda equals 2, find the necessary relationship between U and V if no real solution exists. If no real solution exists, then there must be some sort of contradiction in here. Something will kind of start to mess up. So let's take a wee look at these three equations. I've let lambda equal to 2, and each of them from the question, and we have this. So I've looked here at the minus 2z and the minus z. So I've multiplied the second one here by 2. Giving me 6x minus 4y minus 2z gives me 2w. I'm then doing this, take away this, that gives me 14x plus 7y equals 15 minus 2w. If I times the first one by 7, I get 14x plus 7y equals 7u. So if there is no real solution, then this must mess up. There must be a contradiction, as in if this is the same here, these can't be the same here. So then for no real solutions, 7u cannot equal 15 minus 2w. The third part then says, if lambda equals 2, u equals 1, w equals 4, find the general solution of this system of equations. So that's then what we have here. So I've subbed in those values, lambda 2, u is 1, and w is 4, and I get these three equations. I sort of do the same thing again here. So I do the second one times by 2, 6x minus 4y minus 2z equals 8. And then 3, take away this one here, gives me 14x plus 7y equals 7, and that's consistent with number 1, so we're all good. We want to try and get x, y, and z all in terms of each other. So if we rearrange the first one, we can get y equals 1 minus 2x. So that is y in terms of x. That's all good. If we substitute this then into the second one, so I exchange my y here for a 1 minus 2x, so that gives me 3x minus 2 upon 1 minus 2x minus z equals 4. Multiply that out, rearrange it, I get 7x minus z equals 6, and rearrange that, I get z equals 7x minus 6. So I know x equals x, I know y equals 1 minus 2x, and then I know z equals 7x minus 6. So my general solution then, if I substitute that in then for t, is going to be t 1 minus 2t and 7t minus 6.